Hello, we are going to start with the third lecture, and the topic for today's lecture is Terzaghi'S theory, Terzaghi'S analysis for shallow foundation. Okay, now this particular theory is very backdated and it's applied usually for shallow foundations with the rough base. Now, there are certain assumptions for this theory. First is soil is homogeneous, isotropic, semi-infinite. What is homogeneous? Homogeneous means the properties of the soil are identical at all the places and at all the times. Isotropic means the properties are not changing in any direction. Semi-infinite is that we are considering the depth infinite in the downwards direction and we do not consider the soil in layers. Okay. Now this is applicable for shallow foundations. What do you mean by shallow foundation? Is that the depth of the foundation will be less than the width. It is also applicable for strip footing. Now what is a strip footing? When the length of the foundation is greater than 5 times the width, then it qualifies it to be called as a strip footing. Also, we do not consider sliding because the foundation is rough. We assume that there is no sliding between the foundation and the soil. Also, the shear strength of soil will be represented by Morse-Coulomb criteria. Okay, tau is equal to C plus sigma tan of phi. Elastic zone has straight boundaries inclined at an angle phi to the horizontal. Failure zone is not extended above or beyond the base of footing. Shear resistance of the soil above the base of the footing is neglected. Now why I have made this green is because in our second lecture we were studying the shear failure proposed by Basic for shallow foundation. If you remember, the failure zone was going up near the ground level. But in this case, we assume that the failure zone is only limiting to the horizontal level of the foundation itself. Just to give you all, let's go to this diagram. It was a similar diagram for general shear failure proposed by Basic. Only thing, this failure surface was going near the ground line and we saw a bit of bulging. In case of Terzaghi'S method, we do not assume that the failure plane will go up to the ground level. Okay, so this is one of the primary differences. Now let's go back to the slide that we were discussing. Okay, method of superposition is valid. This is another assumption. What is method of superposition? In the coming slides, later slides, we will understand that ultimate bearing capacity, what is designated by Q suffix F, is basically equation in terms of 3 parameters. First is C, phi, and third is gamma. Now, while calculating this ultimate bearing capacity, we are directly adding all the 3 terms. Okay, I'm just telling you what is superposition in brief. Whereas in reality, when we try to create the similar site conditions or when we try to analyze the soil when it fails, okay, under a shallow foundation with rough base, can we analyze it for each of these criteria separately? Like we find out what is the failure when only C is acting, or the failure when the soil is more of friction soil, or the failure wherein only the density of the soil is going to be considered. All these 3 cases when we independently check, okay, first and foremost their critical surfaces are different. When we add them all together, first assumption, when we say that all these three things will simultaneously act and we assume that failure plane is common, that itself can be a little bit of question. So the assumption that we are making, method of superposition, is in this, because of this assumption, we are likely to get much higher values of ultimate bearing capacity as compared to those which we would have otherwise obtained if we had considered each of these factors independently or individually. Okay. Then the next assumption is passive pressure force has three components: PPC, that is the passive pressure due to cohesion, then PPQ, that is passive pressure produced by the surcharge, then PP gamma, that is passive pressure produced by weight of the shear zone. Okay, and effect of water table is neglected in this analysis. The next assumption is that footing carries concentric and vertical loads. Footing and ground both are horizontal. Limit equilibrium is reached simultaneously at all the points. Complete shear failure is mobilized at all points at the same time. Properties of foundation soil do not change during the shear failure. Usually what happens, if something is settling initially, then it's likely that after certain amount of settlement, the soil layers right below are going to get compacted. So the density and all these parameters will change after initial stage of settlement. But we do not consider that. We do not give the benefit to the soil of getting a little higher density with respect to time. We assume that the properties are going to remain same at all times. That is what we basically mean by the assumption of homogeneous soils. Okay. We also assume that there is no consolidation occurring inside the soil. Foundation is very rigid as compared to that of soil. Okay, rigidity is much higher relative to soil. The limitations of this theory: first, the theory is applicable only to shallow foundation. As the soil compresses, phi increases. This is what I just spoke about, but we don't give that advantage. Okay, so we are giving slightly conservative results. Hence, fully plastic zone may not develop at the assumed phi. All points need not experience the limit equilibrium condition at different loads. Method of superposition is also not acceptable in plastic conditions as the ground is near failure zone. This is what I spoke about, okay, sometime back. And the next slide. Okay, now let's have a look at this slide. Let's give a minute. Now this is what is happening for shallow foundations. Okay, this is general shear failure by Terzaghi'S analysis. Okay, and this is local shear failure. Now what is happening? You have to look at this wedge A, B, D. Okay, the forces acting on this A, B, D are better defined in this figure. What is happening is ultimate bearing capacity QF multiplied by B. This B should be capital. It's basically standing for the width of the foundation. This will be the force on A, B. Okay. Then apart from this, there will be passive pressure acting. This passive pressure is going to be in vertical direction. It's going to make phi with the normal to these planes. Okay, these planes. Okay, AD and BD. PP is going to be making phi with a line which is normal to these inclined planes. These inclined planes are going to make phi with the horizontal. Okay, this is how the analysis is made. And this zone 1, this ABD, is assumed to be in elastic equilibrium, whereas the zone 2, this AED, and similarly DBE1, okay, and BE1 F1, AEF, these zone 2 and 3, there are two zones which are labeled as Roman 2, two zones which are labeled as Roman 3. Okay, these are going to be in plastic equilibrium. Okay, whereas this one is going to be in elastic equilibrium. Now, what is the meaning of plastic equilibrium and elastic equilibrium? In brief, I had told you all, any material, when it is going to be plastic, or ideally plastic material, we had studied this in physics. What usually happens when you apply stress onto any material, the strain also develops. It will start deforming. Okay, in elastic limits, stress is directly proportional to strain. Then the material yields. Okay, now in our case, the material is soil. The soil will yield. Once the soil yields, the deformation will continue, and this time it won't be proportional to the stress increment. Sometimes you may not even require incremental stress. Deformation may just go on continuing in absence of additional stress. You understand? So that is likely to happen, that kind of behavior is likely to be exhibited in these zones, zone 2 and zone 3. Whereas over here, it doesn't happen. Any kind of deformation will require a little bit of increment here. Why do we require that? Because this zone is directly attached to the foundation. It's directly adjacent to the foundation. And here we also have assumed that the surface is rough. So there is going to be enough of addition or friction, a connection between the foundation and the soil. So for it to move downwards, it is necessary that the foundation also has to move. So this is not going to be in plastic equilibrium. But the rest of the 4 zones, these 2, 3 and 2 Roman 2 zones, these are going to be in plastic equilibrium. Okay, if you have any questions on this, please post them. Right? So going ahead, the failure zones do not extend above the horizontal plane passing through the base of the footing. So if you see, it's stopping here. Now which is the horizontal plane passing through the footing? The line indicated here by a dotted line here. So these are not going above, right? Then failure occurs when downward pressure on soil wedge is equal to upward pressure. Downward forces are due to load QF into B and the weight of soil wedge. That weight will be given by 1/4 of gamma B square tan of phi. Upward forces are vertical component of resultant of passive pressure, PP and cohesion. So if you can see which are the downward forces here, the weight of the wedge and QF into B, and which are the upward forces, it will be PP and a component of cohesion. Okay, these are the upward forces. So for equilibrium, what we require? We require that the vertical summation of all the vertical components should be 0. So vertical components are 1/4 gamma B square tan of phi plus QFB, and these are the downward, and upward will be 2PP plus 2C Li sin phi. Now what is Li? Li is the length of the inclined surface, which is given by B by 2 upon cos of phi. Okay. So therefore, our final equation will be QF. I have kept this on one side and I have taken all the other terms on the other side. So QF becomes 2PP BC tan of phi minus 1/4 gamma B square tan of phi.